Current of electricity. This is a topic that's important for 6091 pure physics, 5086 combined science for O levels, and 5105 N levels.
So circuit diagrams will be important for all the electricity topics, for current electricity, for DC circuits, as well as for practical electricity. So you need to know these basic circuit symbols. For the switch, I think it's self-explanatory. The two dots need not be there, right? You do not need to draw the two dots. Obviously, when it's an open door means open circuit, no current is flowing. When the door is closed, then it's a closed circuit and current will be flowing. One single cell drawn with a short and long line. The long line stands for positive and the short line stands for negative. And for batteries, batteries simply mean that there are more than one cells. Okay, power supply, that we will learn later that there will be DC, direct current, and AC, alternating current, okay, supply. For lamps, we have the older symbol, which is like this, showing the filament of the lamp. Sorry, I can't draw a good circle here. But this is the old symbol, right? The new symbol is simply a cross. Okay, then ammeter and voltmeter, it's the letter shows it very clearly. Ammeters must always be connected in series, and ammeters and voltmeters always connected in parallel. Okay, fixed resistor is just a rectangle, right? Don't get confused with the fuse, which has the fuse wire running through it. All right, so fixed resistor, as the word suggests, the resistance is fixed, it cannot change. For a variable resistor, the resistance can change. Another name for it is the rheostat. Potentiometer, we'll learn more about this under the pure science, pure physics syllabus, right? So we'll elaborate it later on. Elaborate on it later on, right? Fuse, we will learn it under the practical electricity. It will blow or melt when the current flowing through it exceeds the fuse rating. Earth connector, we have encountered this symbol when we were learning about static electricity, right? So when it is connected to the earth, you just need to draw these three lines. The LED, light emitting diode, allows current to flow through it in one direction only. When the voltage is of a certain amount, right, there will be a current flow in the direction of the arrow. Thermistor, simply when the temperature is high, the resistance is low, and when the temperature is low, the resistance is high.
Electric current is defined as the rate of flow of electric charge and is measured in amperes. So the formula is I is equal to Q over T, where I stands for the current in amperes, and Q is charge, electric charge in coulombs, capital C, uppercase C, and T is time in seconds. So 1 ampere is equivalent to 1 coulomb per second, 1 coulomb of charge per second. Then we talk about what is conventional current and electron flow. Conventional current is the path that a positive charge would take, which is from the positive terminal of a battery to the negative terminal. So this is what we will usually draw when we draw a circuit. The current will go from positive to negative. We call this the conventional current flow direction. conventional current. Now, however, later on, when after some time, when current was discovered, they discovered that the charge that moved around the circuit was actually negatively charged, the electrons. So it was only later that they discovered that electrons moved in the opposite direction. So that is why, right, we have the electron flow direction, which is from negative to positive, right? So, but usually we will use the conventional current direction. Just bear in mind that electrons actually flow in the opposite direction from negative to positive. In the syllabus, it says relationship charge is equal to current times time over here. So it's actually a rearrangement of what we have learned earlier, right? We have learned that charge is current is the rate of flow of charge. Therefore, if you rearrange it, charge will be equals to current times time, right? So how do we apply it? We have a question here, a current of 0.25 amperes flowing through a lamp, 0.5 hours. Notice that we need to convert this to seconds, right? And okay, we calculate the charge. So Q is equal to I times T. Current I is 0.25 amperes. Time is 0.5 hours. Converted to seconds will be multiplied by 60. Multiplied by 60, right? So the answer will be 0.25. Let me do a quick calculation. Times 50. Times 0.5 times 3,600 equals to 450. The SI unit for charge is Coulomb, capital C, right? Now we'll be talking about e.m.f, electromotive force. Now for the syllabus, pure physics will require this, the definition, but for combined, whether it's O levels or N levels, the definition you do not need to memorize. However, it's good to understand what e.m.f means. It is good to have the complete picture. Okay, so what is e.m.f? It is usually we are talking about the source. So in this case, we have batteries here. So when we take, for example, a voltmeter and I connect it across the batteries here and say it reads 6 volts, right? Now, 6 volts would be the e.m.f of the batteries, the power source here. So what does the definition say? It says that is the work done per unit charge by the source in driving charges around a complete circuit. All right, so when we memorize formulas, let's break it down to parts. All right, so the keywords here, work done, per unit charge, okay, by the source to drive the charges around the complete circuit. So in terms of the formula, right, we write as e.m.f is equal to the work done, W, per unit charge to drive the charges around a complete circuit. So the units here would be for e.m.f in volts, for work done in joules, and for charge, coulombs. Right? So 1 volt is equivalent to 1 joule of work per unit charge or per coulomb. Okay, so when we see 6 volts over here, we are saying that 6 joules of work, right? 6 joules of work is needed to drive 1 unit charge around the complete circuit. Okay, so what is actually EMF? If you want to use the water current as an analogy, we can think of it as the batteries being, say for example, like a slope, okay, like the Wild Wild Wet water slide, right? So let's say we have a slope there, and we can pour water down this slope, and this water runs around, let's say runs around your room in a drain, right? And this current will only flow when there is something that drives it to move. Okay, so in this case, it's like a water pump, or you can think of it as a water slide where there's a difference in potential that is set up, right? So in this case, the analogy would be the gravitational potential energy or gravitational potential store. So when you bring up a bucket of water, you're storing up gravitational potential energy, and when you pour it down, it's converted to kinetic energy, right? So in the same way, the battery stores up, sets up a difference in potential of 6 volts, right? And the charges can then move around the whole circuit because of the difference in potential. There will be a difference in potential of 6 volts on one side and 0 volts on the other side. So current will flow from higher to lower potential. So in other words, EMF is it sets up the difference in potential so that a current will flow through the circuit. So how do we calculate, or how do we determine the EMF when there are more than one cells present? If we have just one cell of 2 volts, when we place them side by side in series, then it will be 2 times of 2 volts, which gives you 4 volts, right? And so on. So what if you place them in parallel? If you place them in parallel, what will happen is that the result, if I were to take a voltmeter and connect it across these two cells in parallel, the reading will still be 2 volts, right? It'll just be like, for example, if you use the illustration, the analogy of water slides, the 6 volt battery will be like 3 water slides, one after another. So each one is 2 volts, and you set up a total of a potential of 6 volts, right? For parallel, it's as if you have two slides side by side, right? Side by side, so it will remain as 2 volts because they are side by side. So in that sense, when you place two cells in parallel, you will not get any additional EMF. However, what do you think, right, would happen if you place two cells in parallel? What would be the purpose of that, since the EMF doesn't increase? Think about it. So we see this very often in certain appliances, such as, I would say, okay, not appliances, but for example, the electric car. Electric vehicles, they have battery cells placed side by side, providing a constant EMF, right? So in this case, we have 2 volts here. So let's imagine that if it's 2 volts, right, of course it's much more than that, but it will be constantly 2 volts, but it will last longer. So in this case, when you have two branches in parallel, it will last twice as long as if you had only one branch. So this is one use of placing cells in parallel. Most of the time, appliances such as torchlight, toy cars, example, right? These will use cells in series, all right, because there is not enough space to store so many batteries. So whatever number or whatever voltage is required, they will just make sure that the batteries are in series. We have learned about e.m.f, electromotive force, which is, in simple terms, the voltage across the power source or the battery. Now we are going to learn about potential difference, which is important for both pure and combined physics. This is actually this potential difference is actually the voltage across the components, right? So for example, here we see that there's 12 volts of e.m.f, right? So this is the e.m.f of the batteries, and we have learned that e.m.f is the work done per unit charge to drive the charges around the complete circuit, right? So e.m.f is always talking about the source, the power source, right? But if you were to take a voltmeter and connect it across the heating coil over here, this voltmeter will also read 12 volts because there are no other components in this circuit. And we wouldn't call this e.m.f because it's not the work done to drive the unit charge around the complete circuit, but it is the work done to drive the unit charge through the component, which is the heating coil in this case. So 12 volts here, we call it the potential difference. Okay, so if you look at the definition here, potential difference across a component in a circuit is the work done per unit charge in driving charges through the component, right? So if you look at the definitions of e.m.f and PD, both of them involve work done per unit charge in driving charges, right? For e.m.f is through the entire circuit. For PD is just through the component. So the formula for PD is very similar to that of the e.m.f. So we have learned previously that e.m.f is the work done per unit charge, right? So for formula, in this case for PD, it is the same. All right, it is the same. It's still work done per unit charge, but in this case, V is the potential difference in volts. Work done and charge remains the same. It's the same as the e.m.f. Okay, so what is the difference again? For e.m.f, it is the PD, it is the voltage of the power source, right? If I connect a voltmeter across the power source, I read 12 volts, that is the e.m.f. If I connect the voltmeter across the component, such as a fixed resistor, a heating coil like this, or a lamp, then that will be the potential difference across that component, right? So basically you can think of it as the battery sets up the difference in potential so that it can be used up by the component, all right? So having said that, how do we apply this formula? We have a question here. The battery has an e.m.f of 12 volts, a current of 0.8 amperes passes through the heater. Notice that it says 0.80, which means that it's emphasizing on two significant figures. All right. So calculate the amount of charge that flows through in 10 minutes. So what are we given? We are given the current, we are given the time, so we can find the charge. Q is equal to I times T. So you get current 0.8 multiplied by the time, which is in minutes. You need to convert that to seconds, SI unit. So you multiply by 60, and we will get, let me get my calculator. Okay, don't need a calculator. we can do this. 480. So 480 coulombs, right? That's for part A. For part B, calculate the work done. So work done is equal to, okay, how do we find work done? We know that the formula for potential difference is work done per unit charge, right? V equal to W over Q. So if we rearrange this, W will be equal to V times Q, right? You bring Q up, you get VQ. So W equals to VQ, and V is 12 volts. Q is what we have found, 480. So this one, we will need the calculator. We have 12 times 480, you get 5760 joules. But since the question is using two significant figures, we will reduce it to 2SF. My stylus is not working. Let me get this working. Give me a minute. Okay, so you get 5,800 joules, 2SF. Right. So notice that. Okay, would you be penalized if you leave your answer as 5760 joules? The answer is no. It will be accepted because it is 3 SF. So 2 or 3 SF will be accepted by Cambridge. But if your answer is in 4 SF or more, then it will not be accepted. So always be alert about the number of significant figures being used. Now I want to point out that if this question were to ask you for the work done straight away without part A, right? How would you do it? Now you can actually use W equal to VQ straight away by plugging in Q equal to IT into Q, which means that you get W equal to V times IT, right? W equal VIT. And you can do this question straight away in one step. All right, to summarize the difference between EMF and potential difference, we can think of it as when you're finding the voltage across the battery or the power source, that is called the EMF. So if this battery is 2 volts, we will say that the EMF is 2 volts. And when you connect the voltmeter across the component, we say the potential difference across the bulb is 2 volts, right? Now, of course, if there are more than one components, for example, if there are 2 bulbs in this case, right, in series, then your EMF, if it's 2 volts, then the PD across each bulb will be 1 volt each, because the sum of the potential differences across the bulbs will be equal to the EMF of the circuit. But we will learn more about this in the subsequent lessons. So to summarize the difference between EMF and PD, EMF is the work done per unit charge by the source. Right? So if you notice the difference in the definition, here it talks about the source for EMF, all right, and driving charges around the complete circuit. Whereas for potential difference is the work done per unit charge in driving charges through the component. All right, the formula is the same. It's still work done per unit charge, but for EMF, it is to drive the charges around a complete circuit. For potential difference, it is the work done to drive per unit, 1 unit charge through the component, right? Then for EMF, it's always associated with the power source or energy source. Then for PD, it's always any 2 points in a circuit. So I can put the voltmeter across the entire 2 bulbs here, which I will get 2 volts, or I can put it across 1 bulb and I will get 1 volt, right? So this is the this is potential difference, right? For the battery is e.m.f. Okay, for e.m.f, that it can be present even when no current is flowing. So for example, if I have a battery and I place a voltmeter across the battery without the battery being connected to anything, it will show you the e.m.f, right? So if the battery is 1.5 volts, it will see 1.5 volts. But for potential difference, it will be 0 when there's no current flowing. So when there's no, in fact, the converse is true. When there's no potential difference, there will be no current, because current flows from high to low potential. So when there's no potential difference, there will be no current flowing. Okay.